This is a quick introduction to snow avalanches. So an avalanche, a snow avalanche is a mass of snow sliding, tumbling, or flowing down an inclined surface, and there's lots of ways to categorize them based on the properties of the snow, the properties of the snowpack, their size, their destructive power. So we're going to review just a few of those things sort of as a precursor to a discussion on snow avalanche dynamics. Snow avalanches have impacts on lots of different stakeholders. One of the primary ones, especially here in the state of Colorado, is the impact on human life. So the CAIC compiles pretty comprehensive avalanche statistics, and the plot over on the left illustrates the total number of U.S. avalanche fatalities by year from 1950-51 season to the 2020-2021 season, and you can see the moving average is the red line that tracks on top of the bar chart. So in general, we've seen a trend increasing the total number of avalanche deaths in the United States over the last 70 years or so. The plot on the right here shows a graphical representation of the similar data, or really the same data, except mapped per state or by state. And you can see sort of the higher density places where you see fatalities are certainly in the Mountain West, including Alaska, much less so in the Northeast. And in Colorado State, we have significantly higher avalanche fatalities than most other states, all other states. Snow avalanches also have significant impact on infrastructure, including both physical structures and roadways. So you see some images here of roads that have been covered by avalanches. This is a significant concern of entities like the Colorado Department of Transportation and other state transportation agencies in the Mountain West. It's been estimated, depending on the exact location of the mountain pass, but for significantly trafficked mountain passes, like some of those in the I-70 corridor and some of those in the I-5 corridor, like Snoqualmie Pass, the economic cost for closures on those passes can be upwards of $1 million per hour. And finally, avalanches also have a lot of indirect costs, including mitigation. So you have lots of different structures depending on if you're operating a ski resort or if you have a town that's adjacent to a avalanche-prone slope. So you can have these snow fences. You can have, especially in Colorado, we have lots of these avalanche tunnels. This one is Red Mountain Pass. This is Juneau, Alaska. There's a variety of different strategies, also in the European Alps, that are expensive and that require maintenance. CDOT in Colorado maintains a lot of active mitigation strategies for many of the roadways and the mountain passes. In addition, there is significant litigation cost especially for injury or death related to avalanches, either in highways or in resort areas. So in the last couple of years, we saw an inadvertent trigger on I-70 that the state of Colorado decided to try to litigate against two individuals who were recreating in the terrain and caused this slab avalanche, which caused I-70 to close, and it caused a significant amount of damage to that zone. There was a recent lawsuit against an avalanche airbag company. There are suits against guides, against resorts, etc. And there are also new insurance policies, newer insurance policies that can cover individuals in case of hazard, but also structures for those that are located near or adjacent to avalanche terrain. When we think about avalanches, in the US there are 9 distinct avalanche types, also known as characters. And I have them broken out by their general icons, at least those that are used by the CAIC in Colorado. Other state agencies and forecast agencies still use these general classifications in the United States, but they may have slightly different icons to represent that avalanche class. Of course, these classifications depend on lots of factors, and what I want you to do is pause the video for 10 or 20 seconds and see if you can think, based on what you've learned in the class so far, what are some of the factors that might differentiate these 9 avalanche characters in the United States. So go ahead and pause the video for a bit and see if you can come up with a couple key factors. So there are lots. Some of the obvious ones, just looking at the names of some of these characters, are the moisture content. So we have a loose dry avalanche, we have a loose wet avalanche, we have a wet slab, we have a storm slab. The density of the snowpack that breaks, so you can have wind abraded, dense snow, you can have storm generated slabs, you can have deep slabs that exist deeper in the snowpack with higher densities. You can have high moisture content wet slabs. And then in addition, you can have the origin of the slide, so you can have these sort of loose point source slides or these large deep slab types, the mechanism of the slide, whether it's a cornice fall or a glide event. So there are a variety of factors here. We'll talk about a couple of them going forward. Which ones of the 9 here do we think are easiest to predict given what we know about these properties of the snowpack? Pause the video for 5-10 seconds, see if you can come up with a list of easiest to hardest here. So generally, the wind slab, storm slab, and loose dry are the most predictable characters of avalanches, and that's because they follow major weather events. And so the weather is a significant predictor, and the risk of these types of avalanches don't last for very long. And so these are fairly acute events. So you have wind slab following major wind events, so based on the topography and the direction and the velocity of the wind, we can get a pretty good sense of where these slabs are, if they're going to form, and where they're going to form. They're also pretty easy to observe with ground observations and going out into the field. Storm slabs similarly occur when you have storms. So there's an acute event, and following that acute event, you have a high risk of storm slab, which decays pretty quickly following the initial event. And then loose dry avalanches are pretty quick are pretty easy to observe as well, because they're typically in loose unconsolidated snow, mostly on the surface, so they're simpler. The ones in the middle here, the ones that are less predictable, are the ones that are lurking underneath the snowpack. So persistent slab starts to develop over time based on dry or wet snow metamorphism or melt-freeze crust, so that's been a significant part of our class. So with a little bit more knowledge of metamorphism, they're a little bit easier to forecast, but they're not triggered by an acute weather event. These things develop over time, and so they require a closer view of the snowpack, and we know that things like persistent slabs, these deeper faceted layers below the surface, they are highly variable depending on slope and aspect and weather and a variety of things, and so there's more diversity in their location. They can be trickier to forecast. Same with the deep persistent slab problem, and similar with loose wet types of avalanche. And then finally, the least predictable are wet slab. So wet slab is when you have a wet avalanche, like a loose wet, except that surface slush layer has actually consolidated and bonded in a way that becomes a little bit more problematic. The top layer is slab-like. Cornice falls are just difficult to predict. Cornices are easy to observe in the field. It's difficult to know when they're going to fall naturally, and of course, they're impossible to know when they'll fall based on a loaded trigger, somebody that stands on top of a cornice. I'll show you some videos here shortly. And the last one here is the glide avalanche, which we'll talk about in a little bit, which requires some liquid water lubrication against a smooth base surface for a slab to slide against. These things can take many days to develop and sometimes don't actually break out. But when they do, they can be fairly destructive because they often break out to the ground. So there are a couple major or general classifications for those 9 characters. And that's the loose versus slab type avalanche, and it's mostly snow density and the form of the starting zone that dictates that differentiation. So for a loose snow avalanche, these are often also known as sluff avalanches or point releases. They are typically comprised of loose or unbonded, unconsolidated snow, powder snow, with much lower density, high SLR, so things like precipitation particles, or in the event where you have an entirely faceted snowpack, you can also have loose snow avalanches. Largely, loose snow is derived from very powdery, high SLR precipitation particles on top of more dense snowpack, but later in the season, if the entire snowpack facets out, you can also get faceted loose snow avalanches that can go all the way to the ground. And these typically originate in a single point in the snowpack, and there's no solid or consolidated slab that evolves. So that's the origin of the name loose snow and also the other name, which is point release. On the flip side, we have slab avalanches, which are typically more destructive, a little bit more dangerous, and those are comprised of more cohesive bonded layers, higher density layers that typically form on top of the less dense layers. And these slabs develop through densification in the form of either general snow metamorphism or wind abrasion and wind pack. So some examples of specific types or characters that fall within these broader classes of loose versus slab. On the left we have dry and wet loose. That simply is dictated by whether or not there's liquid water as a third phase in the snowpack. So those typically occur on sunnier aspects and later in the season. So you have dry point release here, wet loose or wet point release over here. This is adjacent to Mount Tucanakovitz outside of Moab in the LaSalle range in late May. So south face, lots of direct sun, and you can see the shiny layer of the surface of the melt freeze crust. And then you can see these slides all evolving from point sources near or probably adjacent to these warm rocks that are absorbing significantly a higher amount of that shortwave light from the sun. These loose avalanches are typically not as deep. They're less dense and they're less dangerous generally, but they do have the propensity to sweep an individual off their feet and drag them through potentially dangerous terrain. They're typically easier to see and identify and predict. For slab avalanches, I've shown you 4 different characters here. We have the storm slab, which is consolidated storm snow. So as the storm develops and it starts to consolidate the snowpack, it can develop a slab layer. I have a persistent slab picture here. This is somewhere in the San Juans that I took. You can see a fairly deep break. We'll talk about this later. This is called a crown. Bottom left we have the wind slab, so wind direction coming from left to right in the image, creating this cornice here that loaded up some wind abraded particles down in this concavity, which then either triggered naturally or triggered as a result of a cornice fall. Part of that cornice may have broken and then triggered that slab. And then we have wet slab over here, where again we have a cornice, but this is later in the season, so you have liquid water in this snowpack layer that broke out as a wet slab. Glide avalanches are these pretty interesting and unique types that you don't see all the time, but you certainly see it in specific zones. You can see them a lot. Glide avalanches need a smooth bed surface to slide on. Typically, that occurs where you have a ground surface that changes from rough, maybe rock terrain or talus, to something that's smooth, and that's often associated, doesn't have to be, but it can be on top of firn snow, a glaciated surface, icy surfaces, grassy rolls. They occur on convex rolls with smooth surfaces. And what happens is liquid water in the form of either rain or snowmelt percolates down through the snowpack to that smooth interface, and it starts to pool up there and lubricate the interface between the smooth ground and the snowpack on top. And then that snow starts to move because it's pretty wet. You see glide avalanches a lot in wetter systems. It starts to deform and slowly move over the snowpack surface. And so here's kind of a sequence. This is what's called a glide crack. These are actually all glide cracks, and you can see this occurring over several days, starting to move. That's not a glide avalanche, but it's signaling to you that it could break out. The dark layer there is actually the ground surface, the bed surface below. And so what can happen is that entire section can, in some cases, rip out. And you can watch these things evolve, but they're difficult to know if and when they'll go. This is a picture I took in Bear Glacier in Alaska near the Resurrection Bay. And you can see this is the south aspect here, and this is the north aspect here. This is the glacier in the center. And you can see significant glide activity. You can see the exposed bed surface after those glide avalanches have pulled out all the way down to the glacier there. Cornice collapse are the other sort of unique one that doesn't necessarily fit within the simple loose versus slab categorization, but they're quite straightforward to understand. They're just difficult to predict or forecast. And so we've talked pretty extensively about how cornices develop when we talked about snow transport with wind. So you have your windward and leeward side, so you get deposition on the leeward side over here of wind abraded particles that pack more densely than typical dendritic snowfall. So instead of snow metamorphism causing densification, you have the wind effect causing the densification in the lee side of that slope. So there's a couple things that can happen with cornices. You can either trigger them as a person, and that block of snow can be the size of a small car, or larger than a school bus, and that itself can be damaging and problematic as an avalanche type. And so I'll show you a quick video here. This is a snowmobiler approaching the ridge somewhere in the Tetons. They come up over a cornice, and you can see that whole slab start to break. They were very lucky here. But that's a significant hazard to anybody that's downslope of that cornice fall. Just simply by the mass of that very dense snow. You can see that clean fracture to the right, which could cause damage to those below. The other potentially related problem is if cornices naturally release or are the result of a human trigger of some sort, what can happen is that's a really heavy block of snow that can fall on another potentially vulnerable snowpack below it. It could be from wind loading, because again, if a cornice is forming, that means it's wind loading below it on the lee side of that. And so we have a picture here on the lower right, which shows a cornice fall that was triggered by a wind slab, or a cornice fall that triggered a wind slab. So part of the block broke out and then landed, and that pressure, or the force, actually triggered the weak layer below the wind slab and caused that to run, which you see a similar effect in this massive cornice that's forming on the lee side of this very steep face in Alaska. So a quick question that would be, useful to think about here is what differentiates a dry, loose slough slide and when between a storm slab, and when do you transition between the two? And this is a video I took a few years ago somewhere in the North San Juans of a storm slab that I triggered. You can see the crown there. And this was several hundred feet wide on a small convex rollover. And I'll give you some conditions here to think about. So this event was about 36 inches of snow over the course of 48 hours. The precip started in a cold sub-zero environment and ended up warmer near zero over the course of those 2 days. So what was happening to the snow over that duration of temperature change and increasing mass or thickness of the snow? Similarly, you can probably predict that the SLR of the snow is changing over that same duration because of that apparent temperature change. So the early cold dry snow, when we had actually skied this exact same slope the day before, was producing only point release or slough type avalanches, and that was because the snow was high SLR, low density, unbonded, not cohesive, and not slab-like, and so it wasn't risk. But what happened is on the second day, as the snow continued and it added more depth and wetter snow as it ended warm, with the lower SLR, you started to get densification and cohesive slab of snow. So the same exact slope the following day then became prone to a storm slab. So you can imagine the evolution of the loose unconsolidated snow to a storm slab. This is an image that comes from Bruce Tremper's book, Staying Alive in Avalanche Terrain, and I think it's a nice representation of the same idea, where you have avalanche danger or risk as a function of time, and you have this storm event that's highlighted in the plan. And the storm event, you can see in the early stages of the storm, there's not much risk, which is the day one version of the picture that I'm showing you here, where you just have these point release, loose dry avalanches. And then towards the end of that storm, that's when you peak, and that's when you go or you transition between that slough, dry loose slide into and develop an actual cohesive slab or storm slab, which can be significant and problematic, like the video shows here. And then after the faucet turns off here and the storm stops, you can start to see the development of these more persistent forms, persistent weak layers, which is really all of what we talked about in this class in terms of metamorphism. What's happening in the snowpack once the snow is on the ground. And again, that's a function of lots of different variables that are largely oversimplified in this picture here. So there's some specific lingo when it comes to thinking and identifying an avalanche after it has occurred. So I have two pictures really illustrating the same thing. The one on the left, again, comes from Bruce Tremper's book. Where the avalanche actually breaks that face, when it's a slab avalanche, I should say, these are both pictures of slab avalanche anatomy, that sort of abrupt face from the top of the snowpack to the bed surface where the avalanche slid on top of, we call that the crown. And the actual vertical face there we call the crown face. This entire region where the original crack developed and propagated in the snowpack is called the starting zone, and the left and right sides of this region are called the flank. The stalk wall is when you start to have the large amount of debris start to move back on top of the snowpack, and then you can see the debris field move further down along the track. We call this the run-out zone. Some people call it the deposition zone. And then the very tip of the avalanche is called the toe. I like this image on the right. I think it's a nice head-on representation of the same thing here. So generally speaking, especially in the continental U.S., most avalanches occur on mountain slopes that have slope angles between 30 and 45 degrees. So pause the video for 10 seconds or so and see if you can come up with some ideas for why that might be and some factors that might contribute to that that actually might make this a little bit more nuanced given what we know about snow. So of course the properties of snow are wildly different depending on the nature of the snowpack, the season, the aspect, etc. So just using one example, thinking about the moisture content of snow, changes the stickiness, how well the bonding is occurring between the grains, and so and the bonding between layers. And so in maritime snowpacks, which is illustrated over here on the left, where you have coastal environments that are warmer, you have more bonding, typically more liquid water in snow, you can actually start to push avalanches to higher slope angles, and that's simply because the cohesion between layers, because of that bonding effect, is higher. But when you have high, dry snowpacks that are cold, like those in alpine Colorado, we typically don't have well bonded or cohesive snow, especially from recent snowfall, because we don't have much liquid water in the snow. So we don't get much actual sintering between particles until we have more water in the snowpack later in the season. And so our slope angles typically are less extreme than those in the warmer maritime aspects. And of course, there's lots of other factors here that dictate this. So this is a really general range, but once you get too steep, then those slopes tend to just naturally hold less snow, and they tend to naturally avalanche more regularly, and so they're less prone to the human trigger type. And of course, when you get below 30 degrees, there's less propensity for the layers to slide against each other because there's less strain between the layers being developed on lower slope angles. One caveat here is just to consider that terrain never looks like this. You never have this perfectly linear slope angle. More often you have a diverse type of terrain with various concavities and convexities. And so this picture to the right shows you the effects of a convexity on a small slope where you have this rollover that increases steepness, and then you have lack of what's called compressive support in this region where the snow past this sort of middle part wants to move this direction simply because of gravity. And so these are particularly vulnerable locations to break slabs and trigger collapses, especially if you have weak layers underneath the denser slab on top. In terms of avalanche size, there's really two major classifications that are utilized in the United States. There are others that are used in Europe and in Canada. But in the United States, we typically have these two categorizations, which is size relative to path and destructive force. And I have the table plotted up here. So size relative to path, it considers the whole avalanche path into the account and includes both the horizontal and vertical extent, along with the depth of the actual crown face or the fracture itself. Whereas the destructive force, the D scale here, is a measure of the avalanche's potential to inflict damage upon humans or property within that run-out zone. And so I have a couple avalanches pictures for scale here. So this is the same picture I showed before from the Mount Tucanakovitz Basin near Moab. That shows just a lot of these D1 loose wet types of avalanches. Proximate path lengths around 33 feet, relatively harmless unless it were to knock you over some of this terrain. And then down here in the Flathead range, you have an example of a D3, which is significant. Path length is on the order of 3,300 feet. You can see these huge debris fields, massive boulders from the slab that broke up along the way. And if you get all the way down here to a D5, these are the historic type avalanches that you see for zones that can wipe out significant structures and roads and can run out for almost 2 miles here. Okay, finishing up, I want to kind of put some things together based on some of the other snowpack stratigraphy we talked about earlier in the class. So what are some of the key ingredients for a slab avalanche? So looking at a full profile here, temp profile in blue and the hand hardness profile in red, what are some things that are red flags for you in terms of ingredients? What do we need for an avalanche, a slab avalanche, to form and to propagate? Think about that for a few seconds and we'll talk about it. So we've talked extensively about these inverted or upside down snowpacks where you have a higher density slab that exists on top of a lower density weak layer. Those are the recipes here, and we have these pretty dense ice or ice-like layers. We have a fairly dense slab right here that's developed with a low density layer here. We have another very deep low density layer between these two hard layers, and then we have probably some depth hoar down here. So this is a pretty problematic looking snowpack. We have rapid kinetic metamorphism in the top part of the pack, and we have sort of the longer, prolonged, closer to maybe 5 degrees C per meter kinetic metamorphism that's probably driving the depth hoar formation from early snowpack. So we have both the high density, low density. We actually have a couple of these. This could potentially be a slab avalanche that digs deeper into a deep slab avalanche. But we also then need a trigger. So we need some application of force on top of it, whether that's a human or a vehicle, whatever is going to cause the volumetric collapse of one of these lower density layers. That's the recipe for the slab. And so we have not exactly the same snowpack, but something similar where you've got some knife crust down here really hard, you've got some fist hardness depth hoar, and then you have this hard one-finger slab on top. That's a scary looking snowpack that's not very deep, which looks pretty vulnerable to trigger. But these things alone aren't enough to get a slab avalanche to actually propagate and run. So there's a couple other things that we need in addition to this inverted pack and a trigger. We also need sufficient interfacial energy between the layers as they fail. So there needs to be enough energy not simply to initiate the crack, but to actually propagate it from the load site or load source. We need a bed surface, ideally, something that's smooth and hard. Something like this knife hard crust here would be a perfect smooth bed surface. And then we need a sufficient slope. Like I mentioned a couple slides ago, we need something that's steep enough that once you have a sufficient trigger and a volumetric collapse and a bed surface, that the slope can use gravity to carry the slab blocks over that bed surface. All right, so a couple quick things about how to read the avalanche forecast. I'm not going to go into great detail here because this is certainly not the focus of the class, but it's a nice thing to be able to do. So I'm using the CAIC website as an example. So this is just a screenshot from today's avalanche forecast for the state of Colorado. So you can see they have the danger scale down here. This is the North American Avalanche Danger Scale. 5-level colored scale communicates the danger of avalanche to people in the backcountry, and it's a combination of the likelihood, size, and distribution of avalanches based on ground observations, telemetry observations, and a variety of other factors. The website or the app is interactive, so you can click on a particular zone if you plan to recreate there. So this is the North San Juan zone, so I'll click there. That pulls up this pyramid, and the pyramid tells us, or it breaks out the danger scale based on 3 general elevation profiles in that terrain. So we have the below tree line, near tree line, and above tree line zones. So those are significant because we have typically higher tree density, sparser trees, and absent trees, thinner snowpacks, more wind-abraded snow up at the top. And so that's the distinction between these general zones, and you have them broken out specific to that elevation band. Within that forecast in the North San Juans, there is then a prediction of any avalanche problem or character that may be in the forecast. For today, there's only one, but if there are multiple problems present, you'll see them just listed in a vertical order here. So there may be, today's is a persistent slab, but there might also be a storm slab or a wind slab or something else like that. So you have the symbol, which I showed you before, that's for a persistent slab. And then you have this, this rose, which shows you directionality to where that problem would be likely to be found in the elevation. So this is sort of a top-down view of this same pyramid that was shown before, but now it's broken out by the general directions. So you can see here we have a persistent slab problem with moderate danger level in the northwest through northeast bands at and above tree line. And then we have at or above tree line in the alpine here, we also have the problem on eastern slopes. The likelihood of these triggers is possible, and the size, based on the scales we just discussed, is in the very large to large category. What I find to be especially useful, and now that you've taken this class, I think this will be a really nice read, is instead of getting just the simple backcountry avalanche forecast, which was what we were looking at, that's a nice starting place. It's really great to read the discussion of the forecast, and there's typically a couple paragraphs written by one of the forecasters for CAIC. In this particular one, it's really nice description of what's going on in the San Juans over the last couple weeks, what some key observations were, and what led to the description, and what we might expect in the evolution of the snowpack in the next week or so. I like this one too because there's also a representation of one of the pits that was dug in these zones. You can see the higher density layer on a lower density layer. You can see facets that are found down here, a couple millimeters in size. You can see some failure of a CT test here. So this is all super useful information for somebody who's taken this class. You can see an observation of a large natural release in one of the basins of the North San Juans. And then the last thing you can click is the tab over here, Observations and Weather Data. This is great because it categorizes all the avalanche observations in that zone. You can look at the report, you can see all the observations. It'll tell you when it occurred or when it was observed and reported. The elevation higher than tree line here on the northwest. This is a fairly large avalanche, a D 2.5. And you have some field reports and additional weather observations from weather stations in the zone that you've clicked on. So all together, lots of great information here that, along with some pits that you may dig in that zone and just general observations if you're frequenting a zone, often you can build up a pretty good history of what's occurring in the pack.